Hello, this is Mr. White, and this video is on analyzing sinusoid graphs. We're going to look at these particular functions and find the function equations for each one. Later on, when we get to simple harmonic motion, we'll find out how these kinds of functions can be used to model real-world phenomena, such as a mass on an end of a spring bobbing up and down, or a piston going back and forth, or a Ferris wheel going around. But for right now, we'll just focus on the skill of coming up with the function equation. Let's jump into the first one. I'll remind you that when we talk about sinusoids, that could be either sine or cosine, and you truly can choose either one. Remember that sine and cosine are just horizontal translations of each other, so you can pick whichever one you want, but we'll generally find that you often will find one to be preferable over the other. So for example, the one in front of us right now, notice that its y-intercept right here happens to be the top of a mountain, I'll say. It starts at the top of a mountain and then goes down and back up from there, just like a basic cosine graph would, right? So that'll be reason enough for us to go ahead and use the cosine version of the sinusoid equation. That will allow us to not have to bother with the horizontal translation. So let's also go ahead and get that sine version off the screen, and also instead of using y equals, we'll go ahead and use f of x equals. All right, let's take a look at the information provided to us. In addition to the graph itself, we see the graph dimensions, I'll say. We see that on x we go from 0 to 45 pi, and then in the y direction we're going from 0 to 22. Okay, we study the graph a little further. We see those horizontal line divisions. It looks like divides the graph into about 11 different zones. So we'll deduce that each one of those, that we're jumping by 2 in the y direction. And we'll deduce that, let's see, this must be 20 right here at the top of the mountain. Let's see, 18, 16, 14 right here. That'll locate the bottom of the valleys. Now, please avoid the mistake of thinking that either of those numbers, 14 or 20, don't think that that's what the k value is. Remember that the k value, the vertical translation, locates the center line of the sinusoid. The line right here that divides the center line right down the middle, the sinusoid right down the middle, I should say. And where is that center line? There are a couple ways you could kind of think about it in your head, but I generally like to say it's the average of the low and high y values. So off to the side, I would think 14 plus 20 divided by 2, that's going to give me 17. That locates the center line. So that is the k value. I should point out, it doesn't really matter in what order you determine the parameters, A, B, H, and K. Find them in whatever order you feel most comfortable with. But it seems logical to me to go ahead and determine what A is, the amplitude. The amplitude is the height of the mountain. It is also the depth of the valley. We can see that distance between the height of the mountain, that's the distance from 17 to 20, so that's a distance of 3, right? And again, that's the same distance from the depth of the valley, 14, back up to the center line, 17. So our A value is 3. Now we should be open to the possibility that that might actually be a negative 3 under some circumstances, but we know that negative sign is what imparts a reflection across a horizontal axis. So if you had a function that looked more like this, that's where we would expect a negative sign in front, right? In this case, we'll just leave this as positive 3. All right, what about the H parameter, the horizontal translation, also called the phase shift? Well, the reason we chose to use the cosine graph was so that we wouldn't have to do a phase shift, right? So by using cosine, we'll just say that H equals 0, or we can just kind of omit it altogether. And the last parameter we need to find, B, that's the one that generally students have the most trouble with. Be sure you're aware that B is not the period, but it is related to the period of the function. We see several cycles, several periods of the sinusoid on the graph. Let's kind of count them out. There is one period from one mountaintop to the next, one period of the sinusoid. Here goes our second period. And then it looks like just a half period there. So I would write off to the side, and I encourage you to show this in your work. Show that 2.5 periods equals, well, the distance from 0 to 45 pi along the x-axis, right? So 2.5p equals 45 pi. You could just divide both sides by 2.5 if you prefer. I have a slight preference for writing that as an improper fraction. 5 halves p, 5 halves periods equals 45 pi. We'll then multiply both sides by the reciprocal of 5 halves, in other words, by 2/5. That cancels out over here, leaves us with just p. And on the right side of the equation, let's see, 45 divided by 5 is 9, times 2 is 18. So the period is 18 pi. But I remind you again, that period p is not what gets put here where parameter b is, but they are related. Remember, we can think of the period 18 pi as being the result of a basic period. In other words, the period of either just y equals sine x or y equals cosine x by themselves, untransformed, multiplied by some sort of horizontal stretch or shrink. So, how can we stretch a period of 2 pi out to 18 pi? That would be by a horizontal stretch of 9, right? That is related to b. And reminder, it's related in a counterintuitive way. We need to flip it and put a 1/9 here. All right, let's pretty that up a little bit here for our final answer. And I highly, highly, highly recommend that we check on a calculator consistently. Notice that I set the calculator window settings to match the dimensions of the graph that we were, or at least the viewing window of the graph that we were given, 0 to 45 pi on the x, and then 0 to 22. Or actually, how about let's just do 14 to 20, I should say, on the y. That should capture the low and the high points of the graph. Type our equation in there, and when I graph it, it looks very much like what we were given. Of course, I constrained the windows in such a way that it fills our calculator screen. But again, study it enough to convince yourself that that is the correct answer. All right, let's go on to the next one. Okay, once again, we'll start by maybe observing that this graph has a y-intercept that starts this time in the middle of the graph. It doesn't start at a low point down here or a high point up here. It starts right in the middle of the graph. And instead of starting by rising along a mountain, it sinks down into a valley. That's kind of reminds us of a sine wave, right? Although a basic sine wave starts by going up a mountain. So because this is going down into the valley, we're going to assume that there's going to be a negative a value and choose to use the sine equation. That choice, just like on the last example, is what's going to allow us to not have a horizontal translation. So h will essentially be 0. And I'll say it once again, you could use cosine if you prefer, but then you would need a h value, a horizontal translation, aka phase shift. We'll look at the dimensions we're given here. Negative to 10 to 10 on the y. Looks like we're counting by ones here, doesn't it? So let's count off. That looks like negative 1, 2, 3, 4, 5. Negative 5 for the y values for the minima. It looks like positive 8 y values for the maxima. The center line will be halfway in between, and again, I'll use the same method I used last time to find that center line. It's just the average of the low y values and the high y values. So negative 5 plus 8 divided by 2, that's going to give us 3 over 2. You can write 1.5 or 3 over 2. No real strong preference here. That will be our k value, 3 halves. Now the height of this mountain, the distance between 3 halves and 8, that's going to be 6.5 or 13 halves if you prefer. That's the same distance down into the valley, right? So either write 6.5 or 13 halves here as the a, and as we discussed earlier, we'll have a negative sign in front to make this graph start by going into the valley. Now, how many total periods do you see in this picture? It looks like one period there, and then a second period here. So off to the side, I'll write 2 periods equals the total width of that window. 0 to 14 pi is just a width of 14 pi. That means that one period is 7 pi, right? That is longer than our basic period, so we must have had a horizontal stretch. We must have taken our basic period of 2 pi and stretched it out. How much? Well, how about 7 over 2? Just double check the math, convince yourself that this is a true equation. 2 pi times 7 over 2 is what it takes to give us our desired period of 7 pi. And what does that have to do with our equation? Well, again, that horizontal stretch right there, horizontal stretch of 3.5 or 7 over 2, that is the counterintuitive transformation. That means when it gets put into the equation, it becomes 2 over 7. In neatening it up and presenting it here on the screen, I'll show kind of an alternate writing of it, where if you prefer, instead of the improper fractions for the amplitude in vertical translation, if you prefer negative 6.5 and 1.5, that's fine. Although, really want you to just go ahead and keep this 2/7 as a fraction rather than an ugly repeating decimal. And once again, let's check by calculator, make sure we did everything correctly. Set the window settings according to those given to us for this problem, 0 to 14 pi on the x, negative 10 to 10 on the y. Enter our equation. Valley, mountain, 2 whole periods. And you may have noticed that this time I just chose to match the given window dimensions, whereas in the last example I set the y min to line up with the minima and the y max to line up with the maxima. You decide what's going to be most convincing to you to just ensure that you got the right equation in there. I might want to trace or use calcmin or calcmax just to be absolutely sure that the y values of these extrema are what they're supposed to be. I'll leave that up to you. All right, let's do one last example. This one I'm going to do much more quickly than the first two, but there's a particular point I want to make here. Of course, pause and study this if you prefer, but I'm going to just jump right in and say that with the given window dimensions, we could tell that this vertical translation is going to be 10, and that the amplitude is also 10, giving us this height of 20 here, and then we also see that the depth of the valley, the amplitude, is also 10, bringing us to ground level here. And since this sinusoid is starting with a mountain instead of a valley, we'll put a positive 10 for the A value in front. That vertical translation is also 10. We see only one period here spanning the whole width of the window. Now, the width of the window goes from negative 2 x value to positive 8x value. So that's 10, right? And once again, we're going to think of that as a basic period of 2 pi, but this time the period we're looking for doesn't have a pi in it, right? It's just 10, not 10 pi. So that means when we do a horizontal stretch, 2 times 5 gives us the 10, but we'll need over pi to cancel out this pi here. That's going to be our horizontal stretch in this case. And as usual, that will encounter a counterintuitive flip when we put it into the equation. And the last thing I really want to point out here is that notice that the sine wave did not start climbing the mountain at its y-intercept. It didn't start by doing this. Notice there's a translation, a horizontal translation of 2 units to the left. Something like that, right? That's what brings us over to the edge of the window of negative 2. So remember how that's a counterintuitive translation? I'm going a little quickly on this because presumably we're pretty comfortable with transformations back from our earlier studies. But 2 to the left will give us a plus 2 in here, and that's our equation for this function. All right, here it is neatened up. I will leave the check on the calculator up to you, just for time's sake, to keep the video from going any longer. Okay, you know how this goes. Let's go ahead and give you a couple here for you to pause the video and try on your own. Okay, I'm going to trust that you've gone ahead and done these exercises if you chose to, and here come the solutions. Or at least the solutions that I think are the most likely that you chose. If you came up with different solutions using sine instead of cosine or vice versa, and if you checked by calculator and got something that looks like what you were provided, then consider yourself correct. All right, thanks for watching. I'll see you next time.